Then that means we get to talk about science today with astrophysicist Paul Wallace and, average guy Doug Pagitt. That's me coming from Minneapolis.
You're not an average guy.
I'm above average in height. Other than that, just a guy that tries to understand the goodness of the world and science. So, Paul, thank you for being our astrophysicist. Today, we're going to lean into I don't know if we're leaning into astrophysics by talking about Saturn. We're gonna do a little planetary series here on our conversations, and so not only are you an astrophysicist, and I did see you posted something on the social medias, maybe on Twitter, that your associate or interim pastoring status there at the Church in Decatur has changed to permanent. You are now
It only took about 2.5 years, but we got around to it.
Pastor, professor, and astrophysicist. It's quite an author, and best-selling author. I bet you're the best-selling author in your entire family.
I am. Of the five of us.
Yeah, you've outsold them all.
That's true.
All right, okay. So, Paul, we're going to talk about Saturn, and this is your favorite planet.
It is. It's actually in my Twitter bio. I love it so much.
Is that a thing you keep track of, the things that show up in your Twitter bio?
I mean, it's not everything shows up there. My wife doesn't show up there, but Saturn does.
Now, I'm not saying that Twitter is predominantly a male-dominated platform. Does your wife even know that she's not in there, and does she know what you tweet? Does she follow you on Twitter at all?
Not really. No, she's got a Twitter, but she never uses it. No, she doesn't.
Yeah, me either. I really feel like that's just free territory for me to talk about anything I want that Shelley Pagitt would have absolutely no interest.
Yeah, I talk about everything but my wife on there.
On Twitter. Hey, for those that are watching, sorry I've got Paul on here twice because we're without Dan Dietrich, who's our producer today. So it's just Paul and I trying this all on our own. So if things get funky, wonky, silly on the video audio side, just know we're doing the best that we can. All right. So what is it, Paul, about Saturn, and what has been your relationship with Saturn that makes you love it, and why should anybody else possibly care? Like, if people aren't into the moons, the stars, the heavens, what is it about Saturn that's so great?
If you don't, I don't know. I had this conversation once. I'm going to tell a little story here about, I was sitting around a faculty table some years ago at a college, and we were talking, and I was talking about a little bit about physics and stuff. And I said something about relativity, something about relativity. Yeah. And the English professor said, but why would you care? Why is that important? And I just looked at him. It was just like, you just don't, if you got to ask the question, it's already passed you by, and so I feel that way about Saturn. If you have to ask me what's appealing about Saturn, all I would say to you, have you ever seen a picture of Saturn?
Okay, let's pretend that really the most I've seen about Saturn have been in like little books and a simple, flat dimensional photo. I don't know why I've never I know it's the one with rings. So like when you're memorizing the planets, like one is hot and one is red and one has rings. This thing, my little grandson, almost 2, is working on. Venus is his favorite because it's hot.
It is. And bright.
So let's just imagine that, the question has passed me by.
No, I didn't mean you so much, because you're sitting here holding a podcast interested in Saturn. I mean, you're light years ahead of the mentality that I'm
of an English professor. Use me as your foil just in case somebody else is listening along who also is like, I don't know why Saturn. How does it relate to relativity of all things?
It doesn't. It's just the point is that there's a sense of if you haven't been struck by it, then it's just cool. It's just there's a sense in which it's just cool and it's fascinating, it's wonderful, and it's beautiful. I think just the sheer beauty of the planet goes a long way with me. Just the sheer appearance of it. The
Have
fact
you
that
looked at
thing,
Saturn through a telescope?
oh
Have
yeah,
you?
oh yeah, yeah, many
Oh,
times.
really?
And just the sheer fact that that thing even exists, it looks like it was made on like God made it on a big lathe, with all these,
Yeah.
it's just this lovely thing. And I just can't imagine that thing, is really out there, that it's really as large as it is, and that it's, been out there millions of years, and only in the last, couple hundred years have we even gotten to look at it. And it's a lovely, lovely thing to behold. So that's really actually the first and primary reason why I love it. It's not scientific at all. It's purely wonder, which is at the root of science. Of course, wonder is always at the root of science and many other good things. But that's really the actual motivator.
And is it the rings that are really to someone who
Yeah.
glances at Saturn? That's really the thing that captures
the
one's-
rings and the way that the moons of Saturn have created patterns in the rings. The moons and the rings interact, and they're all, I think of them all as one big thing. And the way they have created, I don't know if you've probably heard the term fractal before. But the rings have a fractal quality to them. The closer you look at them, the more you see the same pattern. No matter how deep you go, you see this lovely complex pattern in the rings.
All right, so we've put together a little video here for people to watch about Saturn. And by put it together, I mean I downloaded it off of YouTube and then put it into this presentation, and then we're going to play it. Yeah, but we had to put it together so people could see it today. So we'll take that level of credit. It's like when someone makes homemade or restaurants make house-made foods, and it was really everything else was grown and produced somewhere else, and they just put it all together. But we'll call this house-made here because our images are on this, and maybe we can talk over it a bit as it goes.
Sure.
So it's a 3-minute long thing put together by the good folks over at National Geographic, all about Saturn, and here it is.
With its gold color and stunning rings, Saturn is quite a planetary gem.
I'm going to ask you why it's gold.
Saturn is the second largest of the 8 planets, and it is about 10 times as wide as Earth. Despite its size, Saturn is actually the lightest planet. It is predominantly made of the gases hydrogen and helium, and because of its particular gaseous composition, Saturn is the only planet in the solar system that's less dense than water.
Unbelievable.
If the planet were placed on an enormous ocean, it would be able to float. Saturn's gaseous makeup also means that it has no true surface. At its center, the planet has a dense core of water, ice, and rocky material, but it has no actual landmass.
Come on.
Instead, it's mostly made of gases, liquids, and yellow ammonia crystals that swirl around the planet, creating golden clouds and storms.
How does it hold together?
The largest storm on Saturn is at its North Pole. It's over twice the size of Earth and shaped in a near-perfect hexagon.
How about that?
Each of the 6 sides is believed to be the result of jet streams, which all encircle a massive hurricane. Because of Saturn's inhospitable environment, the planet cannot support life, but some of its moons might. Saturn has more than 50 confirmed moons, and each varies in size and terrain. Enceladus, one of Saturn's smallest moons, is covered in ice and only about as wide as the state of Pennsylvania. Titan, Saturn's largest moon, is nearly as wide as Canada. Titan is also the only moon in the solar system with clouds and a dense atmosphere. Both Titan and Enceladus have underground oceans that would make them potentially capable of sustaining life.
The moons could
Saturn's
sustain life.
moons may also play a role in shaping the planet's signature feature, its rings.
Yay.
Saturn's ring system is the largest and most complex in the entire solar system. The rings are made of icy and rocky remnants from comets, asteroids, and moons.
Come on.
The particles range in size from being as small as dust to as big as mountains. The ring system is divided into 7 groups of rings. Altogether, they are as wide as 4.5 Earths, but only about 2/3 of a mile thick. How the rings are able to stay on track and intact has to do with Saturn's smallest moons. Called shepherding moons, these tiny satellites orbit between the rings, and they seem to use their gravity to shape the ring material into circular paths. Saturn has fascinated
All right,
scientists.
I think that's a good spot. All right, so
Okay.
that's a fantastic little introduction. At about every 4 seconds, I feel like I'm lifting my hat off my head because my brain's
I
exploding.
saw you there.
These are incredible things. All right, so one of the lines that they use in that video, the commentator says the shepherding moons, these small moons, seem to be moving in such a way as to create the ring.
Yeah.
How much of people who study Saturn are feeling like we have a pretty good idea, but we're still not fully there on our understanding of it?
I'm a little mystified by the use of the word "seem" there.
Okay.
Because it's really not a question.
It's locked in. Okay.
It's locked. That's locked in.
All right. So
Yeah,
we've talked a lot about
absolutely.
gravity. Gravity's the essential, essential, I don't know, force that holds all things together that we know are held together. How does Saturn have enough mass to have enough gravity to hold all of this if it's gases and whatever it was, amino acids and other things? Is that all from the core?
ammonia? Yeah.
Yeah.
Most of the mass is in the core, just like the Earth. It's denser the further down you go. So that's certainly true. But even in there's probably a rocky core in Saturn. It's probably quite small relative to Saturn itself. But it's just, I mean, the reason why our atmosphere hangs on to the Earth is gravity. If we turn gravity, we had a big switch on the wall, right, and turn gravity off, we would lose our atmosphere in an instant.
But on Earth, is the ground, the soil, the mountains, all the above surface things, is that not what produces the gravity that holds the atmosphere in place?
Yes and no. I mean, it's 8,000 miles down. I mean, it's the whole thing that does it. It is the stuff that we see, but it's mostly the stuff we don't see that's further down. That's where all the mass of the Earth is. It's down, further down, and that's what does it. Yeah, and Saturn, is just a big ball of gas, but it's hugely massive. I mean, it was a little misleading. I thought it was a strange choice of words again in the video when it said that it was the lightest planet.
Yeah, it could float on water. It could float on our ocean.
It is light, but it's more it's heavier than Earth is. I mean, it's much more massive than Earth is. What the commentator meant to say was it's the least dense. Saturn is far more massive than the Earth is.
Oh,
way
I got
more
you.
massive.
So all of that mass translates into some gravitational effect, some gravitational pull.
Mass is what's responsible for gravity.
Yeah, because I think they said something like it's 10 times the size of Earth. So if our planet was 10 times wider and bigger, would it also be holding these particles around it? So, is that why Saturn holds these particles? Because there's so much mass that when these little exploded comets and moons or whatever get into its place, they sort of get sucked into gravitational magnets.
It's really no different than Earth. It's simply that the mass of the planet is not solid. It's mostly gas. There's a little bit of solid core probably, but it's just mostly gas. And gas is massive too.
Oh, see, I guess that's where in my little brain I have assumed that the gravitational pull has to come from something being solid, because they always talk about the solid core, then that produces the gravitational pull. So I guess I've been assuming that liquids and gases don't have much gravitational pull on another more solid object.
But they do if there's enough of it, like in the case of Saturn. I mean, it's not very dense, but there's so much of it, it produces an enormous gravitational field.
I don't know, that kind of that's sort of amazing. Is this the only planet that's as gaseous as
No, all the four big outer planets are the same way: Jupiter, Saturn, Uranus, and Neptune. They're all basically gas.
And those
You
gases,
you can't go walk. You can't go walking around on them. There's no surface to walk around on.
see that, I mean, with all the moon landers and then the Mars lander, I guess maybe everybody else sort of knew this part. I just assumed that part of a planet was, there was a thing, there was a surface there. If we even created anything that could get to Saturn, it would just would it be nothing definable that would tell you you're on what appears to be the surface?
Yeah, in fact, Cassini, which was a probe that was orbiting Saturn for, I guess, 13 years, 12, 13 years, when it was over, when it was out of, its fuel, essentially, they just let it fall down into Saturn and it burns up. It doesn't land, it doesn't hit anything. It just burns up in the atmosphere and it's gone.
Okay, so when we're looking,
there's no place for it to land.
So we can't see gases, right?
Sure, we can. You can see Saturn, right?
Well, that's what I was going to ask you. What are we seeing when you look at Saturn and we see its shape, not its rings, but the shape of the circular thing?
Yeah.
What are we seeing? Water droplets?
Mostly hydrogen gas.
You can see it.
You can see it. If it's dense enough, you can see it. And it's also got a little helium in it, and it's got some ammonia, and that's what gives it the yellow color, is ammonia.
Ammonia.
Yeah.
All right. So these gases, when they're all is there anything on Earth that is similar to that? Like, is there a time where we look at something and we can see these gases
No, because the atmosphere is totally transparent, but I'm trying to think of a gas that would.
Our other senses find my gases, if you know what I'm saying.
I can't, I'm coming up blank on that. I'm sure there's a case I can come up with, but off the top of my head, no.
All right. So
it's really that it's just dense enough and there's so much of it that we can't see through it. So
even gases can be more or less dense.
Oh, yeah.
I just need a second to sit with that for a minute. Like, it just feels like if there's like more and more. Okay, because somewhere there's an outer edge to where the gases aren't there. So what creates that edge is the gravitational pull.
Yeah, and remember that Venus is not. Saturn and all the other planets are not moving through a gas; they're moving through a vacuum. Space is a vacuum, so there's nothing to rip the gas off of it as it moves around.
Say that again.
Okay.
Almost exactly this.
One question that often I'm answering a question you didn't ask, but it's a question that I'm hearing because my students ask it a lot, which is how can the gas stay on it if it's moving around the sun so fast?
Well, that's a better
how does it not just blow off?
Yes.
Right. And what I say to them is that Saturn is moving through a vacuum where there is nothing to rip the gas off of it. And that's the same with the Earth and its atmosphere. It's moving through a vacuum. That's why the Earth can maintain its atmosphere.
Oh man, is that helpful? Okay, because there's not anything else pulling the gases away, the amount of gravity that it takes to hold those gases together can be less.
Yeah.
Or
right.
Yeah.
Right.
Okay. I think you're being gentle with me.
The gravity is sufficient to keep it together, and there's nothing ripping it off. There's nothing.
Yeah.
It's not like it's passing through air at so many thousands of miles per minute.
I see. It's passing
through nothing.
Vacuum. Yeah, through nothing.
Vacuum. Space. Yeah.
Jim Eaton is asking: could Saturn be a planet that's in form? Like it's forming, like, is that possible that it's going to start coalescing into something that looks like the other, more hard?
No, it's more or less, it's more or less in its final state. It's still changing. All planets are still changing to some degree, but we'll have some comets fall into it and it'll probably lose its rings eventually. But
that's sad.
It's
yeah.
Not
in our lifetime though. We're not going to see like little
other planets
rings of Saturn.
Other planets will get rings. It seems that in a few tens of millions of years, Mars might have a nice ring. So rings, we believe, over long enough time scales just kind of come and go.
Because they just
we think they're not permanent.
Like they're just attracting enough comet dust and
they're
Teslas that are floating around up there going to get sucked in there.
Yeah,
and all,
lost socks, whatever. Airline luggage, that disappears.
All the things like all the things we're shooting up into space and just leaving up there. Are those going to get sucked into the rings of Saturn someday?
No, Saturn's the rings of Saturn and the main rings of Saturn are almost certainly created by comets that get too close to the planet and are torn up by its gravitational field, that are ripped apart essentially by its gravitational field.
All right, I'm just going to leave the fact that there's a gravitational field that's produced by gases in that part of my brain that I know is true and I don't understand, which isn't like the category of electricity. I still don't really understand how electricity comes out of my outlet when I plug something in. But,
but by the way, the sun is also not solid, so it's not just.
Yeah, I guess yes, of course, I knew that it's a star, and the gravitational pull of the star is what keeps the Earth in its orbit. Right.
Yeah.
So of course I knew that. But I don't know. It just feels like the sun is always this little exception to.
I get that. I totally get that.
Yeah. All right. And so just to be back to basics, because I had to remind myself this morning, the difference between a planet and a moon is that a planet revolves around the sun,
right?
And the moon revolves around the planet.
That's right.
And that could be the only difference. So you could have a moon that is life producing and a planet that's not.
Yes.
And so, which I think to a lot of our experiences, we think, oh, the Earth as a planet is sort of life producing and a moon is like this just rocky thing that's whipping around out there.
Right.
But in this case, that doesn't have to be the case. It could be, the other way around.
Yeah. So Jupiter has a couple of moons that we think are interesting and may be able to harbor life, and so does Saturn. But the planets themselves, only if life is completely other than what we think it is, only if it's much more general than we think it is, we don't think that Saturn or Jupiter could maintain any life.
Which I guess is helpful for people that haven't studied astrophysics since ninth grade. That the difference between a moon and a planet is our designation of what it is orbiting around.
Right.
That it's not in kind or something. It's not
exactly.
It's not the material. It's the relationship to a star or the relationship to the planet.
It's all context. Yep.
Yeah, which now brings us back to the conversation with the English professor in that story you told. So now we're in, and the philosophers come in, and we're like,
yeah.
The reality of all of this is just constructed narratives of relationality. Okay, so we already talked about why it's gold, and that's because we somehow can see the what'd you say?
It's got trace amounts of ammonia in it, and that's what happens to look yellowish.
And where does it get its color? Like, is it the sun that's bouncing? Like, doesn't it need light? Okay, so it
does. Yeah. If we turn the sun off, we wouldn't see any of the planets.
Got it. So it's not a star. Like, I mean, there's nothing about that gas that's burning itself. There's no burning of any of this. Yes. Okay.
No, but if you dump more gas onto Jupiter or Saturn and the outer planet and made them bigger, just dump more and more hydrogen gas onto it, they would eventually become stars. The composition of the sun and the composition of Jupiter and Saturn are basically the same. It's the same thing. It's just that one of them is so massive that its core is hot enough to ignite fusion. It's not a matter of material. It's a matter of scale. That's all it is.
This is so helpful. So the difference between a moon and a planet and the difference between a planet and a star is not necessarily the makeup.
Right.
It's size and relationality.
Yep. And so basically Jupiter and the sun are materially speaking the same thing, but one of them is a lot bigger and gets hot enough to sustain fusion in its core. That's the only difference.
Now, if you have not put that on a quiz for your physics students, sort of a trick question, that no, they're made up of the same things. I don't
they
know
that.
They do.
They get that from me. Yeah, absolutely.
And okay, so you obviously make a big deal out of that with these you teach not only advanced students but freshmen.
Sort of astronomy 101. Yeah.
Why is it important that you make a point out of that with your students and you make a point out of that with us? Why is that?
I just think it's weird because you wouldn't expect it. I just think it seems unlikely that Jupiter or something like Saturn even and the sun are basically the same thing. But, size matters, as they say. And once you get to a certain threshold, the temperature in the core gets hot enough and it changes everything. You start creating, new elements inside the core. And so you get a star.
Okay, so think about where a star comes from. It's this compounding of all these gases that get pulled together. Again, I'm not totally sure, and maybe you can tell me, whatever initiated that first gravitational pull from the star. I don't know what does that. I mean, I get that once there's enough size, then there's some gravitational pull, but how does that start? Well, let's start there. How does that start? Like, how did Saturn or the star or something have enough mass?
Yeah. Well, the solar system, the whole thing basically has a common source. It wasn't built up of disparate things from here and there. It came out of one big.
The voice of God is what you're going to say, right?
Yeah, voice of God, basically, in the form of a big cloud of dust and gas.
Okay.
That eventually, for some reason, this I believe is the question you're asking, got dense enough to start to collapse due to its own gravity.
Yes.
Yes, and that could happen by a number of ways. It could happen by the most obvious thing that could happen is a nearby supernova creates a huge shock wave.
And pushes a bunch of...
That sounds rare and exotic, but supernovas are going off in the universe, in the galaxy all the time. It's not that
we
weird.
should call them regular novas, like standard novas, like daily novas.
Even a regular nova could do it, which is a thing. There is a nova and there's a supernova. I don't know if you know that.
What's the difference between a nova and a supernova? The size? Is it size?
Yeah. Basically, it has to do with the mass of the star that's dying. Both of them represent dying stars, but the mass, the larger the star, the more likely it is to end in what we call a supernova.
We just, in the English language, we just love to use the word super for things.
We do.
It's shocking how often it shows up, right? It's like and sometimes used in very precise terms, but then you're like, it's just really big,
and then beyond that, there's hyper. There's also a thing called a hypernova. So
it's like running around all the time, won't stop asking questions. Yeah, fiddling, fidgeting all the time out in space, tapping its foot.
Yeah, exactly.
Hyper. Oh, okay, so somehow, big explosion in the cosmos.
So let's say a supernova goes off, which kind of begs the question because the supernova presumes another star was formed. But
sure,
huge shockwave could, and I don't know if you've seen pictures of nebulas, but there's gas and dust everywhere in the disk of our galaxy. It's just everywhere. And if you get a nice supernova go off, it could compress one of these clouds of dust and gas, and once if it reaches a certain sort of critical density, it will start to collapse in on itself.
Wow. What is a supernova? What force is it? It's not gravity that it's, I don't know. Is it gravity that is sending? Like what is then the force of a supernova?
It's related to gravity, but essentially, in fact it is. It's partially nuclear as well. It's essentially a nuclear explosion that was driven by gravity. That's
because there's no
helpful.
Atmosphere. Like I know all space is vacuum. So why? So something is moving through the vacuum that's gathering up these particles.
Think of a really massive star that blows off 90% of its mass at a good fraction of the speed of light.
Okay.
And it started off really massive, like 20 times the mass of the sun or something. It's blowing off 18 times the mass of the sun in all directions, moving, appreciable fraction of the speed of light. So it's a pretty severe, it's a pretty intense event. And so that material rushes out through space in the form of a big shock wave.
And that shock wave is moving just through the atmosphere?
No, it's just moving through space. The shock wave is composed of stuff.
The shock wave is composed of stuff. It's not just a force. Okay.
Right. There has to be a medium, right? And it's being carried out through the material itself. The material itself is rushing outwards.
And then it has enough speed or gravity that it starts attracting other things to it, and that.
No, suppose this shock wave comes through the scene, but right in the middle, you had this big cloud of dust and gas hanging out, and then the shock wave moves through. It's going to compress one side of it before the other side feels it. It's going to basically compress it like a car hitting a wall.
Okay.
The back of the car keeps moving. It's going to compress the thing. And when that happens, the cloud of dust and gas, which was formerly kind of all thinned out and very large, gets compressed into a smaller volume. And then the gravity can take over because it's now small enough to collapse by its own gravity. Before it wasn't. And that can lead and often does lead to the formation of many stars when one of these clouds of gas and dust collapses. The more it collapses now, Doug, the faster it's going to collapse, because the smaller it gets, the more tightly it pulls in on itself. So it's kind of a positive feedback thing. Once it starts, there's no stopping it. It's automatic. It'll just go. It doesn't require any more. And so what you get from that is usually a star cluster, anywhere between 20 and, a million stars, depending.
Wow.
So stars are born in litters and like puppies, right? They're born in groups. They're not born as individuals.
And A Star Is Born, especially the new version, is just the greatest movie, and the soundtrack.
I've not seen it. I know that Lady Gaga can't do anything without you falling in love with it.
You said Star Is Born, and I nearly started tearing up, just right here. Okay, so back to Saturn. It has that fractal cloud storm that's been swirling for millions of years in that hexagon shape. And if people are only listening on the podcast audio side, to watch this video, you can just search for what is Saturn on YouTube, and you'll see this video that we played, and it shows this hexagon shape of this this hurricane that is moving. Curious word, because hurricanes have to do with oceans, I thought. But anyway.
I thought that was a little bit odd too, to call it a hurricane.
We should really just make our own our own video.
It is in the sense that it is a hurricane in the sense that it's a big rotating storm. I think that's why. Got it. But listeners can also just Google if they want to see better pictures. I mean, the picture in that was okay, but I've seen more clear ones. If you just Google Saturn hexagon, and then look at images, you'll find some really phenomenal ones. And
those were taken from that space rover or whatever that was flying around that they finally crashed. Is that the only one up? Do we have anything up there now that's watching not
around Saturn? The storm? No. But we only know that storm has persisted for about 30 years, so we don't really know it's been going on longer than that. We don't know how long it's been persisted.
Oh, that's interesting. So it's not an assumption that just kind of came with the formation of Saturn and the rings.
No, it maybe like the rings themselves. Maybe it's got a lifetime.
Okay, interesting.
We don't know.
And so that's water, right? So I'm kind of getting back to our consistent water question as you take a drink of water. Perfect timing. So we get back to our water question because water is necessary for the kind of life that we would describe as life.
Yes.
So the makeup of certain particles of hydrogen and oxygen have to be in place. So there's water. There's water floating around up there. And again,
not on Saturn. Not on Saturn. There's very little.
What is that storm? That storm is not water?
No, it's hydrogen, helium, and ammonia mostly.
It's a hydrogen helium storm. See, here's a thing that just as a confession, and maybe helpful to people who talk about this. When someone says they're storm clouds, people like me tend to think that's water.
I understand that. That's perfectly understandable.
If anyone else thought that it wasn't that it was a storm cloud of the very same elements that are the makeup, good for you. You're an A+ student. So water's not a part of the mix.
No,
of Saturn. It is part of the moons. It's the center of the moons.
now there
but not
you
the
go.
center
Yeah,
of Saturn.
there's water on some of its moons for sure.
Wow.
Yep. So Saturn, is actually. I will throw this in now. It feels like a good place to throw this in. That there's almost certainly pretty much a constant rain in the upper atmosphere of Saturn. But the rain is not water; it's helium. It's falling.
But helium floats, Paul. We all have those balloons. Helium floats. Don't try to trick people
doesn't go
here.
down; it goes up.
There's no falling helium.
I had never even thought of that before.
All right, so let's just pause there for a second. Helium in our atmosphere is lighter than our air, but helium in the Saturn atmosphere is not lighter than its atmosphere.
Because it becomes liquid, it's cold enough to actually condense like rain, like water does here.
Wow.
If the pressures and the temperatures are low enough, it'll condense. Helium will condense into drops in Saturn's atmosphere the same way H2O condenses into drops in our atmosphere.
How cold is it out there? Do we know how cold those?
Yeah, the upper atmosphere of Saturn, I don't know. I'm going to make I don't have the numbers in front of me. I'm going to guess 50, 60 kelvins, which is like negative 220 degrees Celsius, something like that. Is really cold.
Can you speak Fahrenheit? Kelvin, Celsius.
No, I
Fahrenheit.
can't. I actually can't.
It's like asking how many ounces are in a 2-liter bottle of Coke. No idea how many ounces are in 2 liters.
No, I have no idea what that is in Fahrenheit. I don't think Fahrenheit.
Okay. It's
unless we're talking about the weather.
Because once you're talking physics, you're using the other system totally. There's no need to translate that into the few people left.
Okay, here we go. I got it. I got it for you.
Oh, you did. You had the book. You had a book sitting right by you that allows you to translate.
Yeah, I got a book. No, they actually translate for me, which is really nice. It's my Physics 101. Astronomy 101 book. It's negative 300 degrees Fahrenheit.
Okay. So it takes that kind of there's no temperature on Earth that we can even manufacture to get something
not even close.
Where helium's going to get to a liquid state. Which I guess is one of the things for us to think about here is these planets, the norm on these planets are of a scale that is really outside of anything in our human experience.
Yes.
And maybe this is the struggle that so many of us have with science, whether it's looking at the stars in the sky or the rings of Saturn or how a vaccine works. Yeah. It feels like it's outside of our human experiences and the things we know. So we have to create another category that we don't see anywhere other than when we're talking about that category.
Yeah,
and that strikes me.
More so, it's a matter of taking the categories that we have and expanding them into a more general, more general, you know what I'm saying? I mean, we understand pressure and temperature, and on Saturn, the pressures and temperatures are still pressures and temperatures. They're just the numbers are just not what we're used to dealing with. But the definitions of pressures and temperatures are the same categories. They're just off the map as far as we're concerned.
Right. And I think that's one of the things that if people struggle with science, I think one of the reasons is that so many of us just struggle with ever extrapolating one experience we have into scale. Right. So
Yeah.
I think of this when someone, has their first baby in their family, and then they're gonna talk about having another one. They're like, "There's no way I could have enough love for another baby until that baby comes." All of a sudden you find out, oh no, you did. Or we're doing this bike ride across the country, the We the People ride, and we're going to be riding, 50 miles average a day. And one of the people that's going to ride the whole way with us said to me yesterday, he said, like, I've been riding, kind of getting ready. I'm kind of, I ride about 25 miles. And then a little while later, he said, I just keep thinking, how could I possibly double that? And, and then do that day after day. It's what people, if they're, are in run a half marathon, then think that was so hard. I couldn't possibly run another. We have a hard time as human beings moving from what we've experienced into a imagined
it's a large
version of what's not, even if it's built on the same thing. And I have a feeling that some of us are more capable, comfortable, and satisfied at doing that. We can live in that imagined space. And I don't mean that you've made it up. I mean as imagined as compared to experienced in that imagined space. And others of us have a harder time living in that imagined space. And it feels like that's one of the differentiations between people who easily get concepts or understand science or something, and those who don't.
Yeah. You have to generalize everyday experience to a larger kind of field.
Yeah.
And see that what we experience every day is just a special case, it's just a special case of this more general thing.
Yeah. It's like when I'm around musicians and I'm like, okay, I can think of music that I have heard. You can think of music that's never existed. Like you made it. Yeah. That just differentiates. I don't know. It differentiates the musicians from the non-musicians. I don't know how you put a finger on it.
Not only with music, but with art and with anything, writing, novels, so forth. It's like that ability to sort of live in a dimension that I just don't have access to. I just don't have access to that. And that just always amazes me. Always amazes me.
Me too. And this is the human, and the different human beings are much more comfortable, capable, and affable, or not affable, or can acquire this so much easier than others. And I don't know it. So I don't know what we do about that when it comes to science, because there's some people who probably have already stopped listening. Like, I just don't even, I can't even think about these things in these categories. And then you get into theoretical physics.
Yeah,
like now we're just really making stuff up.
Yeah.
It might be true. It might be real.
It feels like that, but the physics is always tied to experiment, and it's amazing to me that you can do that you can get so far out on a theoretical limb. And say, well, it's got to be this way because nature's got to be this way because other things are true, and so you're way out there. Then all of a sudden, 20 years later, they do an experiment, and you were exactly right, even though you were so far out on a limb and you sounded so crazy to everybody else. Over and over and over again in the history of science, that's happened.
Says every QAnon believer I've ever spoken to. You think we're crazy?
Wait and see.
Okay, I had some. There was something. How do we? So on that route, how do we know at what temperature? Let's just say helium. We know that it can turn to liquid at X temperature, but we don't have any way of doing that here because we can't get something.
We make liquid helium all the time.
Oh, we do. So we can produce 300 degrees.
We can produce that temperature.
Fahrenheit.
In fact, at the pressure of the Earth's surface, at we'll call atmospheric pressure, you can only get liquid helium like at negative, I don't know, way colder than Saturn. It's like 2 or 3 kelvins, which is like, I don't know what that is Fahrenheit, but it's way colder than Saturn. But we can produce liquid helium at those even colder temperatures. And we can produce liquid helium like it's produced on Saturn, just not in the same quantities. We can produce liquid helium. It's just not easy to do. You can't go down to Elements R Us and buy very cheaply. I mean, you can buy liquid helium, but it requires a lot of effort to make, and it requires a lot of effort to keep it. And I
want to go to Elements R Us and pick it up.
Yeah, it's a great store. We got one here in Atlanta.
Okay, so yeah, run by the CDC. So
Yeah.
part of the magic of Earth is that it just happens to have a a makeup of elements that allow life to, as we
Yeah.
know it, to flourish. And as
The
far as we
temperature
know,
here is just right for water to be both to be at the in all three phases, solid, liquid, and gas. Um,
um, okay. And is there any reason we know why some planets attract some elements? So, some ammonium,
yeah,
uh,
hydrogen,
why
helium.
can I, hydrogen, helium, and ammonia,
Yeah,
that's what it is,
yeah.
and ammonia. And then here in our atmosphere, it's different. Is there something about those elements, those gases, that would be more attracted to something the size of Earth, and there's something the size of
Yeah.
Saturn that attracts all of those? Like, why is there so much of some on Saturn and just the right amount for life here,
Two
short
things.
of, the
Two
hand of
things.
God? Yeah.
The first thing is gravity, and the
Yes.
second thing is temperature. Okay, let me just here you go. Here's your educational moment. Okay, the hotter things are, the hotter the air is, for example, the faster the air molecules are moving. That's all temperature is. Okay, so the hotter a thing is, the faster its molecules are moving around.
All right.
So a hot day, a hot windless, it doesn't matter if it's windy or not. A hot day, the air molecules are moving faster than on a cold day.
That's what makes it hot.
Yes, that's what heat is. That's what temperature is.
So when someone
That's
goes
all that it is.
outside and they're like, hey, it's, hot in the sun, it's because the molecules on their skin or on any surface are starting to move faster.
Yep, the molecules in the air are moving faster. Difference
Okay.
between a cold air and hot air, the only difference is
How
that the hot
fast
air molecules are moving faster.
And what causes them to move faster?
Energy from the sun, sunlight.
Okay.
In the summer, the sun's up more, it's up longer, and the sunlight's more direct. So the air has more time to absorb the energy from the sun. And that means it moves faster,
Okay.
which means it feels hotter.
Got it.
Got it? Okay. Now, next thing you need to know is that if the Earth if we had helium in our atmosphere,
Which we don't.
okay, which we don't. If we ever did, even way back in the cosmic past, if we ever had hydrogen and helium in our atmosphere, which are the two major components of Saturn and Jupiter and so forth, if we ever had hydrogen and helium in our atmosphere, it would be so warm that those little molecules would move so fast that they would escape the Earth. Gravity. They're moving too fast to be held by the Earth. Light molecules move faster than heavy ones.
Because of the gravitational pull of the gravitational pull of the Earth is too small.
Too small.
Got it.
To hold those small molecules, which if you've got a mixed gas of like oxygen and helium, and it's at a given temperature, say 70 degrees Fahrenheit, the helium molecules are moving much faster than the oxygen.
So any helium molecules that kind of got near Earth would be moving still so fast they would leave.
They would
the
escape the Earth's gravity. They would achieve what we call escape velocity, and they would leave.
I'm in some relationships that I want to achieve escape velocity. So that's a great concept. All right. Okay. So
that's all it is. It's the Earth's gravity is not sufficient to hold them at the temperature this close to the sun.
So we have helium on our planet. We just don't have it in our atmosphere.
Yeah, it's very, very uncommon. There is some that's being created in the upper atmosphere, but it's very rare.
How do we have it in balloons? And we
can extract it from the air. It takes some effort, but we've got
so it's
the process
in the air
down.
Okay.
Yeah. So yeah, I mean, when I say it's rare, there's plenty of helium in the room where you are right now. It's in there.
But compared to Saturn, you're saying?
Yeah. Yeah.
Yeah.
I don't know, 1 part in a trillion. I don't know what it is. But even one
Oh.
part in a trillion, there's still trillions of helium molecules in the room where you are. Even if there's only one per every trillion particles, there's still
I see.
trillions of them.
Is
So
there oxygen? Is there oxygen on Saturn? Is it mostly
I
oxygen
don't,
free?
not that I know of. I don't think there's any oxygen.
So why is that? So we can have a small amount of our gravitational pull is sufficient to hold small amounts of helium in our atmosphere. And
Yes, but it's got to be replenished, and it gets replenished from volcanoes and so forth because we're always losing it. It's got to come
so
from somewhere. Yeah,
that was going to be my question. Where is it coming from? You're saying it's down deep in the molten makeup of lava that then comes out in gases.
well, when all the ash and stuff, volcano blows, all the gases it blows out, there's some helium there. Not much.
So there's more. Okay. So even the helium that we have in our air, these little trillions of molecules, those are also at some point just going to escape and get out of our atmosphere. Yeah, are we going to run out of helium at some point? Is this a new worry that I should be having? That
not this month. Not this month.
Okay.
Anytime. No, I think we're okay. We're good.
Are there other gases that move at such a speed that the Earth's gravitational force?
Hydrogen. I don't know how much H2 there is in the Earth's atmosphere. Lithium is also pretty light. No.
So there's an abundance of these things that are in this underground, in the middle of the Earth somewhere.
And I wouldn't call it abundance. There's still trace amounts of it. And
but there's enough to replace. There has been for 4 billion years, or whatever, enough to replace what would be escaping from reaching the.
Eventually, we'll lose it. I mean, volcanoes. Over time, there's fewer and fewer volcanoes on Earth over a long enough span of time because the Earth cools down. But that's really long scale. Way more than this month.
The sun's going to burn out before that. Is this place going to go?
I think volcanism will slow down appreciably in the next billion years or so, and we still got a couple billion until the sun burns out. So, I suspect the volcanoes will slow down first.
Paul Wallace, the volcanoes will get us before the sun burns out. Happy Friday, everybody.
Asteroids will get us first.
Is that right?
Oh,
the asteroid's going to collide into us again and send us into another ice age.
Mathematical certainty. It's just a question of when. Not this month, though, Doug. Don't worry about it.
Well, how do you know? How do you,
we're working on it. We're working on it.
You say that because we would know if an asteroid that was big enough to cause serious damage to the Earth was anywhere nearby. Like that couldn't sneak up on us, right?
It happened. I'm not sure if we would know it in enough time. It depends on how long we wait. If we'll have enough time to do something about it.
How does global warming fit into all of this? What we're talking about? I mean, I know we talk about carbon dioxide increases, and that's warming the atmosphere. Is there anything else that we learned from Saturn that tells us about our own pattern of? Like, should people think about global warming in relationship to these hot and cold things that we're talking about with these other planets?
I don't think so. I think it's such a unique situation that we're in.
It's really our atmosphere that's heating up.
Yeah, it's really our atmosphere is heating up because basically when you get more CO2 in the atmosphere, remember I told you earlier about how the difference between hot air and cold air, basically. Yes. Basically, CO2 absorbs sunlight very easily. And so when it absorbs sunlight so easily, it gets moving faster. That's what it means to absorb the sunlight. That's where the sunlight goes. It goes from radiation of the sun into what we call kinetic energy of the molecules moving around. And so CO2 is really good at doing that. And so that's why when you have a lot of CO2, you have a lot of heat. Because it absorbs if you get so much energy.
I see.
A lot of that sunlight. So if you've got a sample of nitrogen and a sample of CO2, and you shine the same amount of sunlight on both of them,
wow,
the CO2 will raise in temperature far faster than the nitrogen will.
That is such a great explanation one step further about why CO2 in the atmosphere causes global warming, because
Yep.
its molecules translate the radiation from the sun into heat, because its molecules start moving so much faster than.
Yep. It's a very efficient transfer of energy with CO2 relative to things like oxygen and nitrogen. Yeah. It's just the quirk of the molecule. That's all.
Looking at these other planets also kind of makes Earth even more stunningly impressive. Do you feel that way? Like somebody who studies
absolutely. Yeah, absolutely.
Like I know, geologists and chemists and biologists and they all get to kind of focus on Earth. And then sometimes astrophysicists, people think, are staring off into space, and why don't you care about Earth? But actually, it makes this.
It's like traveling to a different country, Oh, you come back, like, oh my God, language is a miracle, for example,
That's right.
or whatever.
So is a properly cooked pasta. I mean, it just really blows your mind.
And a nice espresso after dinner.
Yes.
But yeah, it just really lets you see the Earth much more clearly and with much more appreciation. We got to take care of it, man. I mean, this is the one. It's literally 1 in a trillion. We really got to take care of it.
Okay, so to the people, we'll just end on this climate change and global warming, global weirding moment we're in. There are people who hear all of this and they say, and these aren't the ones that are saying like God's going to just protect the Earth from human endeavors. Don't worry, God's got a plan. Not saying that, but just thinking about all the other things we talked about, from supernovas to the gravitational pull of gases and all. There's people who, like, they believe that global climate change is caused by human beings. But I know a lot of people who are very committed to that reality, and also like, but are we really caught? Like, does our small little footprint of, like, when you look at the planet and where people live, like, are we really able to impact this entire system to the degree that people are saying? I feel like there's still a skepticism in there somewhere. Like,
I'll tell you what it is. And I can go back to the analogy, the picture that I just drew with the two gases, with CO2 and with, say, oxygen. You got two gases. If you increase the density of CO2 by 0.5%, the temperature change is not 0.5%. It's nonlinear. It goes up very quickly. As you increase the CO2 in the atmosphere, say you double it. That's too much. Say you increase it by 1%. That doesn't mean a 1% temperature change. That means a far larger percentage temperature change. It's not a linear system. A small change can produce huge effects, and it doesn't require us to triple the amount of CO2 in the air to get triple the temperature.
Got it. So the planet is not particularly fragile, because this is the conversation that people get into. Is sometimes people want to advocate for caring for the planet. We'll talk about its fragility. You're saying, well, the planet's not fragile. Well, tell me if you've been agreeing with this. The planet's not fragile, but CO2 is so capable of producing heat that small amounts of that will just produce an oversized amount of heat, knowing that a small amount of heat adjustment in the Earth can have significant impact, like 1 and 2 degrees temperature wise,
enormous,
is enormous in that sense.
And the planet is not fragile. We could not destroy life on this planet. We could not. The Earth has gone through so much worse than anything we could ever throw at it.
That's a good point.
The point is it going to be habitable for us?
Yes.
Because life will survive no matter what we do.
Yeah.
We might not. And we might end up killing 9/10 of us. But life itself, Earth is not. Life in general is not fragile. Specific forms of life might be, but life writ large is extremely robust.
Well, that's even interesting, and maybe that should be some of the way that people talk about global climate change, right? Because sometimes it's talked about as if human beings need to protect the Earth because we don't want to destroy the Earth. I mean, that's straight up quotes, right?
Now
And
that
so, like,
is that is impossible. In the sense, these people you were saying a moment ago said we couldn't possibly make that big of a difference.
Yes, they're right about that. But we could make it uninhabitable for
Us,
other living creatures, including us, and we might be already
us.
doing that, so that some creatures that live, some living beings are not able to live, and it could tip in such a way, because for human life as we know it to be sustainable on Earth, a certain set of conditions have to be in place, and that could change.
That could change, and if we wipe ourselves out, we'll take a lot of species with us. But in the long term, that's going to give evolution a great opportunity to create a whole bunch of more life that it never thought of before. And there would be over enough time, there'd be this enormous explosion of life long after we were gone, of new forms of life that we couldn't even imagine. The biggest explosions of diversity have always come after big die-offs, always.
And you're not advocating for that.
No,
you're just saying
I'm not.
That's how the system.
I'm just saying that life on Earth is going to survive us. The question
I thought you were about to say, and that's the theme of the novel that I am now writing, the futuristic novel about the future life on Earth that came out. Well, Paul, I know
vibe there too. Life after death. I mean,
see, yeah,
really
the greatest time.
The most creative work evolution does has always been after major extinction events. Always. It's weird.
It's probably, as you say, that's probably also true in the individual in that fractal-like way. That's also true in the individual, that when those things in your life change, die, go away, it's a moment of life.
Yep.
In some other space that often looks unrecognizable, but still there. Well, Paul, I know we don't pay tuition, like the good students at St. Agnes, and we don't pay your salary like the high rollers there, indicated. But we appreciate you being our astrophysicist here, the astrophysicist of the scientist of the common good.
It's always fun talking to you, Doug.
Thanks all. Hey friends, keep up on our podcast, on our website for all the stuff we have going on over at Vote Common Good. And if you want to be part of this little bike ride, we're going to ride across the country. Because I'll tell you, you want to see a part of Earth that doesn't look like what you thought it looked like, come along the border with us and look at not only the landscape, the geography, and then what human beings have done by building a ridiculous wall to separate human beings and butterflies from each other. It will, it'll let you know that we don't just live on this planet. We actually create realities around this planet. So, hey, Paul, I don't know if I've told you, we make a big point about the fact that we're bike riding, and certainly we invite people to ride with us. There's also at least 3 different opportunities for people to join us without riding at all and to go into Mexico. Like, we're going to go into Nogales, Mexico from Nogales, Arizona, just south of Tucson. And we're going to spend time at a center where asylum seekers and refugees are, and we're going to stay overnight there and spend time with these people and get to know them. So if you've ever thought, I want to personalize my experience around these issues of the border, that's something we're
that's exciting.
So yeah, it's going to be pretty great.
And you're doing it 2 other places also, not just Nogales?
Yeah, then we're also doing that over in Agua Prieta, which is by Douglas, Arizona, and then we're doing it in El Paso, and we're going to do it down in McAllen, and we're going to do it over in Tijuana. Yeah, so different experiences in different places. We'll be crossing the border a number of times that we find ourselves there.
That's lovely, man. That's going to be a great time.
And, not only interesting to you, but maybe to others that are listening as well. So, hey, thanks all, and we will talk to you on Monday. Thanks, Paul.
Sure.